CLion, a cross-platform IDE for C and C++. Download now.
Well, good afternoon. I hope some more wander in, but I'm going to get started here. Welcome to Alex Stepanov, Generic Programming in the STL. So the premise of this talk is that you'll be a better C++ programmer and a better STL programmer if you have an idea about where the STL came from and what the intentions of the creator was. So we're going to talk a lot about Alex Stepanov. He is the mind behind generic programming, the standard template library, and the book Elements of Programming. And I'm going to lay it out right now and let you know, it's going to be easy for you to tell. He's my idol, right? So there's no hiding that. I have a great deal of respect for Alex. And it comes from the fact that he asked a particular question. And the question was, can we write algorithms generically, by which he meant we could then use them without having to rewrite them, without loss of performance? And the interesting and perhaps sad thing about this is that nobody really asked this question before, or if they'd asked it, they hadn't really attempted to answer it. And this is really what Alex's career was, is answering this question. And in fact, the other sad part is that in order to answer this question, which has really only had attempt to answers in two languages, C++ and D. Both of them have some versions of the standard template library, and both of those languages had to be significantly modified in order to make that possible, which means we have languages out there that people are doing, real serious professional work in that can't answer that question. So Alex, and I'm calling this the legend of Alex Stepanov because part of what I'm going to tell you are things that were told to me and I can't really verify them. And I'm not absolutely certain they were true, and I'm not absolutely certain I remember them correctly. So I don't really want to be the definitive source on Alex's biography. I have confirmed that he was born in Moscow in 1950. At a very early age, he was identified as a mathematically gifted individual, a mathematical genius. And this, of course, the Soviet Union during the Cold War was very much about being competitive and getting athletes to gold medal and chess masters and musicians and whatever could raise the status of the Soviet Union. And so mathematicians, genius mathematicians, were given educational opportunities. And Alex, and I want to emphasize this, Alex thought of himself as a mathematician. I mean, sometimes he said, I'm not a programmer. Of course, obviously he was a programmer, but he thought of himself first as a mathematician. This was his training, this was his orientation. But his specialty within mathematics was the mathematics of computation. So that's why he was interested in algorithms. And that's why he asked the question that I said earlier. He was also interested in doing things that were practical. So there was a mathematician, Hardy. Hardy had said, he actually apologized. He said, math should be for math's sake. And I apologize if anybody takes my mathematics and try to do something practical with it. But that's not the way Alex thought about it. Alex said, Hardy's hope is that his mathematics is never going to be applied, is not for me. Alex very much wanted the work that he did to have practical relevance. When he was finished with school, he worked there in Moscow. He worked on a hydroelectric power station automation team. And he credits this with an awful lot of practical information about what it takes to be a programmer and real-time operating systems and reliable code. Because as he pointed out in an interview, it's really not easy to reboot a hydroelectric power station. So reliable code is a prerequisite there. So Alex came to the US, and this is what I can't really verify. My understanding is that when he came to the US, the Soviet Union revoked his degrees. So he was given the equivalent of what we would call a PhD as a late teen or as an early 20-year-old in his early 20s. He was, as I said, very academically gifted. But when he left the Soviet Union, they stripped him of his degrees. Now, I'll tell you right now, if I own a degree and you say, well, we're taking it back, no. It's on my resume, right? But Alex didn't do that. And in fact, one of the things that you'll notice as I go through, he had an academic position once as in Polytechnic University in Brooklyn. But other than that, he never worked in academia. He worked instead in industry as a research scientist in industry. But my conversations with Alex were such that he very much revered the academy. He was all about the academy. A number of things he said you could tell. He was very academic in his approach, very respectful of the academy. And I have to believe that the reason that he didn't pursue an academic career was because effectively all his academic credentials were taken from him. And so that's why he was working in industry. In fact, when I knew Alex, I was chairing 2 different C++ conferences, the C++ Now and the CPPCon. I begged Alex to come and speak at either of these conferences, and he just wasn't interested. They weren't academic conferences. They were professional practice conferences, and he just didn't have time for that. If they had been academic conferences, he would have, I'm certain he would have been happy to join us. When he, his next position was for General Electric, and he worked on he created a language called Tecton, and he was focusing on algorithms defined on algebraic theories. Again, this mathematical basis for thinking about programming. So this language was a functional language, and it had no practical results. And I want to emphasize that's not my opinion, that's what Alex said. But he said he learned something important during this time, and that was that complexity assertions have to be part of the interface. And you have to understand that this was pretty much contra to how people were thinking at the time. People were, in fact, talking about abstract base types. And an abstract base type would define an API with the implementation being responsible for performance. But Alex said that's not really good enough. We need to think about complexity in terms of the interface. We'll talk more about that. While he was at Polytechnic, he worked on a library of data structures and algorithms in Scheme, and then he was asked to create a generic algorithms library using Ada generics. In 1987, he did about a year at Bell Labs, and he worked on an algorithms library in C++, which did become part of, they called it the standard C++ components for Unix. At this time, of course, there was no standard for C++. There's no ISO standard. But versions of Unix were shipping, and they would ship with a library that included some of his algorithms. He tried to get Bjarne to add generics or something like Ada's generics to C++. At this time, there was no templates in C++. So he was trying to get Bjarne to add that so that he could try to do a generic algorithm library in C++. Alex moved on then to HP Labs and spent 4 years on storage systems, basically learning to program drive controllers. But in 1992, he was given the opportunity to go back to research. He was still at HP, but they were allowing him to do research. And he was going to do it in C++ because now C++ had templates. And one of the things that he said is that he tried to get Bjarne to add templates in the way Ada did, and Bjarne didn't. Bjarne went off his own way. And Alex was very glad he did, because he said the way that Bjarne implemented templates allowed him to do things that he couldn't do in Ada. So it was during then, in 1992, then he started working on what would eventually become the STL, which was a generic library in C++. Also, while he was at HP, he got a chance to meet with Andrew Koenig. So Andrew Koenig was the chair of the library subcommittee of the Standards Committee. Andrew had met him at Bell Labs. Andrew was a very, very early C++ programmer and very influential in the standard. My understanding is that his name was the only name to be in the standard because they had Koenig lookup, which they've now renamed, but anyway. And Andrew, with his wife Barbara Moo, would come to Stanford every summer and teach a class. And because HP was located in the Bay Area, Alex was in the Bay Area, they connected. And because Alex was now working on the C++ library, he showed Andrew what he was working on, and Andrew was very impressed. So Andrew invited Alex to make a presentation at the Standards Committee. And this presentation, which I've seen the slides too, and I'll show you how you can get the slides. It wasn't focused on his library. It was just about types in general and logicking and reasoning about types. Alex remembers this as being well received, but a little dry. But then in 1994, Andrew sent this email to Alex and said, you know, if you're going to make a submission to the Standards Committee for them to accept your library, the deadline would be this date, which was about 19 days away. Alex said no. But he gave reasons. He said, look, here's the thing. He said, my library would be the largest proposal the Library Committee and maybe the Standards Committee in general had ever seen. So casting your mind back, at this time, the only thing that the Library Committee, or I shouldn't say the only thing, the big things the Library Committee had done was they accepted the C library by reference. It's like, okay, the C standard is part of the C++ standard now. And they had done the string class, and they had done I/O streams. That was pretty much it at the time. And Alex is looking at that and looking at his library and saying, this is going to be huge. It'll be overwhelming to them, right? The other thing is, he said also, they're just about to ship the standard. Well, this was in 1994, so it was another 4 years before they shipped the standard, but nobody thought that at the time. Everybody thought, well, it's just, we're going to wrap this up in a few months. But it also turned out that the previous meeting, the ISO committee, had voted to not accept any more major papers. They were saying, we're trying to ship this thing, no more major papers. But perhaps the biggest argument that Alex made is, he said, the committee's not going to understand my work. And you understand, that wasn't arrogance. You have to understand the world at the time. This was the 90s, the mid-90s, and object-oriented programming was the solution, right? Because what had happened was people who pay for software to be developed would pay to have engineers create an application. And they say, wow, that's great. Now I want a similar application that does something different, but in the same domain. And you can reuse some of this code, right? And the engineers are saying, well, those functions kind of do what we need for that. It's not going to be easy to reuse that. And so people were starting to think in terms of libraries and functions written in a way that could be reused. But object-oriented programming, now that was the solution to code reuse, because you're not really focusing on the functions, you're focusing on the objects. So you can write objects in an application and then take those objects and then use them in another application. We have a great deal of code reuse. So that's the way people were thinking at the time. Everybody was excited about object-oriented programming. The premier language for object-oriented programming was C++, and that's what programmers in C++ at the time were doing. And Alex was not a fan of object-oriented programming, and he didn't do any object-oriented programming, and his library was not object-oriented. It didn't use virtual functions. In fact, it had standalone functions for things like begin, end, size, and empty. These were things that when he finally made his proposal, he made them member functions. And when I talked about it, he said, well, it was, I don't think he even proposed it otherwise and got pushback. He said he knew that's what the committee was going to expect. Now you see that we start to have begin, end, and size as standalone generic functions, because it's a more generic approach. And the committee understands that now, but he didn't think they would in 1994. And of course, it was template-based. When I first started using C++, I contacted a more experienced engineer that I knew had worked with C++. And I said, hey, I'm starting on a new project, and they're using C++. What should I know about C++? And he was upbeat. He said, oh, that's great. There's a lot of great stuff. It's going to be great. And he says, there's two things you need to stay away from, though. Exceptions and templates. And that wasn't terrible advice, partly because people didn't really understand either of those. And the tools were probably not implementing these consistently. There were some performance issues with both of those. So that's what people were staying away from. So here we had this situation where Alex is saying, my proposal, the committee's not going to smile at anyway. And I completely understand this. When I first heard the STL had been accepted, I was at that time a freelance programmer. And again, this was back when software didn't get pushed to the server every week. No, that's not how we did work. We put software on a little round thing that was in a little square thing that got sold for money in a store or maybe through the mail. That's how software was, which meant that there was a 9-month or a year-long process to create an application. And that's what I would do. I would get hired, I would do the 9 months, and then I'd get hired somewhere else and go somewhere else and do another application. And if it happened to be using the same object-oriented framework, great. I was, had a leg up. I knew how the utilities worked, I knew how the framework worked. But if it was a different framework, then I was starting all over, getting up to speed, not just on a new domain, but also how the object-oriented framework was working. And so the idea for me to use the standard template library, which I knew of, had all these standard containers, that was very empowering for me because I could go from project to project and have a lot of knowledge about containers going from project to project. And I want to point out then that when I sat down and played with this, I had a tutorial, take me through, okay, here's what we're going to do. We're going to create a value and we're going to put it in vector. We're going to call pushback and put it in vector. So now it's in vector. I said, no, it's not. It's right here. A copy of it is vector, but the item's right here. You see, the paradigm, we're used to it now. We've been using the STL for years. Some of you have maybe never seen the C++ before it had the STL in it. So we think about it that way. But understand, how does a container work in an object-oriented framework? What does it mean to have a container of objects? Well, what that means is that you have a container which we would think of as a vector of base class pointers, right? So putting an item in a container, what does that mean? That means you copy the address into the container, but more importantly, you transfer ownership to this container so that if the container is deleted, it's going to call delete on all of those pointers. You see, we had a different idea about what it means to put something in a container. And so, again, this was just not the way Alex was thinking about things at all. And people who were object-oriented programmers, C++ programmers, this was a research library. Alex was happy to show it to anyone. And they were all impressed. It's very logical and it makes sense together, but often the response is, I'm not really sure how I'd use that. I was still motivated to try to figure out why everybody was excited about this library. And I don't mean this in an afternoon. I mean, this took literally years for me to kind of get to. At some point, I was, trying to figure it out and thinking, well, maybe I'll learn by looking at the source code. Yeah, it turns out that if you don't know a lot about templates, and maybe even if you do know a lot about templates, you're not going to figure out the logic of this library by looking at the headers, right? But I remember reading an interview with Alex where he was talking a lot about algorithms. And I thought, that's the secret to the library. It's about the algorithms. So I looked, what are the algorithms? Hey, there's sort. Single, simple command that will efficiently sort whatever data you have in whatever container. That is amazing. How handy is that? Now I look to see what other algorithms we have. Well, we have find. Find starts at one end and just sees if the value's there. It's not really overwhelmingly wonderful algorithm. It's like, who hasn't written find, right? I've probably written find, half a dozen times. And that's kind of when it dawned on me. Oh, I see. I shouldn't write find half a dozen times. I've got it right here. That's the power. That's what he was trying to accomplish. But he turned down Alex's invitation, or Andrew's invitation. He said to Andrew, no, for all these reasons, it doesn't make sense to do this. And Andrew then said, I agree. The committee is not going to accept your proposal if you don't make it. So Alex knew what he needed to do, and he and Ming Li on his team spent the next 19 days. He said they worked 80-hour weeks, but the issue was that the library was a lot of code because they wanted to show proof of concept that it worked, but there wasn't much documentation. So they struggled to get it all put together. They got a lot of help from Bjarne, and they got help from Andrew Koenig, and Alex was very much about giving credit to people on the standards committee that helped get this process through. And as we know, it was eventually accepted. So then Alex moved on to Silicon Graphics, where Silicon Graphics allowed him to recruit a team to implement the standard template library and expand it. So that's where the SGI STL is. He worked for a while at Compact, and then he worked in Adobe's Advanced Technology Group under Sean Parent. And then he went to A9, which is a subsidiary of Amazon. And that's where I got to know him. Now, I had met Alex once because he did do a talk at a conference that I was helping to organize. What a surprise. And I got a chance to introduce him. So I had met him, but I didn't really know him. But what happened is I was looking for a new opportunity. I talked to Sean. I said, I'm looking for a company that takes C++ very seriously, because I'd have been a Mac programmer and Apple seemed to be getting away from C++, and I didn't know where to go. And Sean had said, well, Alex went to A9, so they probably take C++ very seriously. So I contacted A9 and sent him a resume. I talked to a recruiter and I said, well, by the way, the reason is Alex is at your company, and that sounds like a good place to be. And they actually arranged for me, when I showed up, he was there to he didn't sit in on the interview, but I just got to meet him again, and that was terrific. And I'd like to say that I worked with him, but the truth is, of course, he was working in research, and I was working on the search engine, the Amazon search engine. That's what A9 does. So if you're interested in any of Alex's material, Sean has tried to get all of his papers, talks, slides, anything he could, and put them in Stepanov papers. There's a bunch of stuff there. If you're interested in the slides for the presentation he made to the standards committee, those slides are there. There's a lot of information there. And then he wrote a few books. The two probably most important are Elements of Programming, and then also From Mathematics to Generic Programming. Elements of Programming is a book that breaks down programming in a very, very mathematical way and builds back up from low-level axioms. So I'm not going to dwell greatly on, we're talking about generic programming, but not going to drill a lot in it. I do want to give you some high level. I want to talk about the fact that when doing generic programming, we don't invent algorithms, we discover them. The way that you develop algorithms is to look for them in code and then see similarities. So if you're doing a sort, you find, oh, here's a string sort over here, and here's another kind of sort, and here's another kind of sort. You look to see what is the essence of these things? How are they written? What is key to them, and distill that. So we're basically trying to find algorithms in the most general form so that they can be reused. But one important concept for Alex always was that we're going to respect the underlying machine model so that we have efficiency. Because again, Alex wants his library to be used, and part of the original question was not just, can we write algorithms so they can be used a lot, but so they can be used without trading off performance. And so Alex was once at a panel, and this is a panel of smart people from a number of different programming languages, and Alex said, well, the only languages worth studying are C and C++. And of course, this delighted the other participants on the panel. But his reasoning was, he says, C and C++ are based on the way the machine actually works. There's no virtual machine that says this is how we wish the machine worked because that's easier for programmers. No, we're trying to capture what is the C machine, what does the standard machine actually look like? Not with specifics to a machine, but just how computers in general think. And the other thing is actually delivering on code reuse, right? So this was the issue with C++, with object-oriented programming. We thought, oh, that's going to solve the problem of code reuse. But it turns out that you can, in fact, reuse the objects you create as long as you stay within that same object-oriented framework. So as long as we're in that situation, yes, we can take objects from one application and use them in another application. But if you have a different object-oriented framework, it turns out those objects are of no use to you at all, except maybe as inspiration for design. And that was a huge constraint for code reuse. But in generic programming, we follow some conventions. You write code that operates with other code without being coupled with it. And that is where we get real code reuse. So I mentioned earlier, Alex said, complexities in assertions have to be part of the interface. So I want to talk about vector push front. The thing about vector push front is there's no such thing as vector push front. Why not? Vector's this container, just like list or deck. List and deck have push front. Why does vector not have push front? Why not? Right, it's the complexity. I mean, it's trivial to implement, right? It's not that, oops, forgot that call, hope we can get it in. No. It's that the promise with push front is that it's constant time. And Alex talked about this in an interview where he specifically picked the stack. He said, if I create a stack library, but it turns out that as you add more and more items in the stack, those accesses slow down, that's not going to make users happy. That's just unacceptable. And so it turns out that part of your interface, part of what you talk about when you talk about an API is delivering on the performance, specifically on the order. All right, so another mandate from Alex was we don't do work and throw it away. Now I want to point out that he did not say always return the work we do to the user. Now that may sound pretty similar, but there's some important distinctions that come out here. So first I'm going to give you an example where we do just in fact return the work. So here is an interface for copy. It's the wrong interface, but here's how it looks. Copy takes 3 iterators. The first 2 define the input range. These are the items we're going to copy from. And the convention in the STL, I'm sure you guys all know this, but I'm going to state it, is the first iterator points to the first element, and the last or the end iterator points one past the last, not to the last. And I'm sure this is counterintuitive to people when they first use the STL, but when you start using it very long, you really quickly get comfortable with that pattern because it just works so often. You start working on a problem and you realize, oh, that's exactly the right solution. The one past just works. But then the third is the output. Where are we going to copy to? But notice there's not a fourth iterator here. There's not a fourth parameter. Why not? Well, it turns out we are actually going to figure out where it's going to copy to based on the fact that there's a certain number of items we're copying from. When we copy all those items, that's where we stop, right? Okay. What's wrong with this interface? I'm sorry? What information should we send back?
Where is it?
Is that lovely? All right. Well, there's more information you can return to the user.
Sure.
Particularly, you want to say, if you're iterating through something, you want to say, well, where did it get copied to? What's the next thing you might want to write to?
Right. It's very likely that the user that's written to an output buffer is going to write some more stuff to the output buffer. And where do they want to start writing it? Well, they want to start at wherever we stopped in our copy. So there's work that we have done to figure out where's the endpoint. And now, could the caller figure that out? Probably. The caller could do a distance calculation on the first 2 iterators and then do an advance on the output iterator, and maybe that's constant time, but notice it's work we did. We figured out where's the end. So this is how we should use the API for this. We return the output iterator, which is one past the last item we copied. Does that make sense? All right. Now this is what I said, is we do work, we return it to the user. But that's not always the way to do it. So I want to talk about the set theoretic algorithms. So just yell out, what are some of the set theoretic algorithms? Set union, what? Set intersection, what else? Set difference. There's 2 more, there's 5. Symmetric difference. And the other one is includes, is one a subset of the other. Okay, all right. So stepping back from code for a minute and just talk about sets generally from a mathematical point of view, do sets need to be ordered? Let me ask you this question. Suppose I told you I'm going to give you 2 sets and I want you to perform an intersection. There's apple, pear, banana, banana and pear. What's the intersection? Banana and pear and banana, that's right, that's right. Now, I didn't give you those in sorted order. In fact, I'm not certain what it means to sort. What is the sorted order, right? It's not clear that that's even sortable. So from a mathematical point of view, a set doesn't need to be sorted and it doesn't need to be sortable. But the STL requires that the input ranges for all our set theoretic algorithms be sorted, right? Now, the question is, does this help the implementation? Yeah. Suppose I ask you, and I'm not going to, this is not a workshop, I'm not going to ask you to do any real work here, but suppose I ask you to write set intersection for 2 input ranges, and I'm guaranteeing that they're ordered. Is that hard to do? Does everybody know how to do that, right? We have iterators to the first of the range. We see if they're the same. If they are, we write it to the output. If not, then we take the smaller one and increment that and then repeat, right? Everybody see that, right? And what would the order of that operation be? The complexity, what would that be? Linear, that's right. Very straightforward, very cool. Okay, now, suppose I told you we need to write this now and we don't have the guarantee that the data is sorted. What now? Right, you sort it first. That's going to be the best way to do this, right? No?
Extra memory will use a hash. I'm serious. Yeah. Because this gives me still a linear algorithm.
Okay.
Extra linear memory.
Okay. So the problem with that, there's a couple of ways we could do this. One is we could tell the user that we are going to sort your data. You call set intersection with these 2 ranges, and we're going to sort that for you. Now, there's a couple of problems with that. One is we don't really want to have side effects to the data that we're operating on, and related to that is the fact then that means you can't find the intersection of const data. Do you see that that's quite a limitation, right? We don't want that. Right? So what could we do? Well, what we could do is, what Dietmar suggested, we could, I wasn't even thinking about it using a hash table, that's right. I was just thinking that we could certainly create a couple of indexes and sort the data and then do our linear pass with the sorted data. But again, this is violating Alex's mandate because it would be doing work and throwing it away, right? And so Alex solved this problem with a very interesting technique. He didn't require that the input ranges be sorted to make the job easier, right? He has access to sorting code. He could do this. Or he also had hash tables. He could do that. The reason that he had the require the sorting is because he wanted the user to do the work. Why? It's not laziness on the part of the library. It's that if the user does the work, then the user knows they have sorted data now. And they can call multiple set theoretic operations, or they can call something with binary search or something like that. Do you see the idea? So the idea is he's not doing the work and passing it back. Instead, he's recognizing that he needs to write the algorithm in such a way that it doesn't need to do any work that will be thrown away, and therefore puts the burden on the caller to do the sorting. All right. So if you talk to your mathematician friend and you say, well, we have this data structure in C++ called set, the mathematician is going to say, well, that's cool. And you say, and it keeps things sorted. The mathematician's going to say, well, again, set doesn't have to be sorted. In fact, it's not clear it has to be sortable, right? But Alex is a mathematician. He knew that. But he also knew that from a practical point of view, if you're going to do computations, you need this sorted. And so the very perfect thing for set theoretic operations is something that both maintains order and also doesn't allow duplicates. So that's why set is called set. It's the perfect thing for doing set theoretic operations. Now, if you really want to blow your mathematician's mind, tell them about multiset. Because from the mathematician's point of view, something's either in the set or it's not in the set. We don't have things in the set multiple times. But of course, again, Alex was simply recognizing that there are times when we have to solve problems where data may have duplicates, right? Okay. So what STL algorithms use binary search? Go ahead, shout it out. Binary search, great. All right. What else? I'm sorry? Lower bound, okay. Upper bound, what else? Equal range. Boy, I paid you well, didn't I? And then, what's the other one, Guy? Not partition, but you missed the point. You missed the point, yeah. All right, so what is partition? Well, partition, we always want to say sorts, but it doesn't sort, it just reorders. It's a mutating algorithm which takes your input range and given a predicate, what's a predicate? Predicate is simply something that either returns a bool or something convertible to bool. So it applies the predicate to everything in the range and reorders such that all the things for which the predicate returns true are before all the things for which the predicate returns false, right? Okay, now, what's that? That's partition, yes. And what does partition return? The partition point, not necessarily in the middle, but you get the idea. It is what? It is the last item that's true, one past the last item that's true, and the first item that's false. You see how nicely that convention works, right? It doesn't matter whether, if I have done this and I have, products that failed quality, well, maybe I want all the products that succeed because I have to ship them, or maybe I want all the ones that fail because they need to be fixed. And either way, I don't have to change the partition point. The partition point is both the end of one range and the beginning of another because of this weird convention of the one past. Okay, so how about if we were asked to write partition point? Pretty trivial little algorithm, right? Given data that we guarantee is partitioned, what's the partition point? We just start at one end and apply the predicate until you get false, right? What's wrong with that, Deemer?
Linear instead of
Right, it's linear, but we could do better. We could do logarithmic with binary search. Okay, great. All right, so in Alex's submission, his original submission only had these three algorithms. It may have had partition point, but I don't think so. It certainly wasn't accepted by the standard committee. Only these three. It didn't have binary search. Notice all of these have something in common, and that is that they all return iterators. Equal range actually returns a pair of iterators. Why are they returning iterators? Well, because what's the work being done? The work being done is finding that value, right? Or finding the position where the value would be. That's the work being done. Whether or not the value that's in the range is the one you're looking for, that's a constant time, a simple little thing we can do. The work being done is finding that location. And so that's what Alex was working on, is the algorithm does work, and we return the work to the user. So why was binary search added? Well, the first question is, what does binary search do? What does it return? Returns true or false. This reminds me of my wife. When I say to my wife, have you seen my keys? And she says, yes. This turns out to be less helpful than you might imagine. Why? Because the important work is being thrown away, right? So this is clearly not Alex's algorithm. He wouldn't have written an algorithm like this because it does work and throws it away. So why was it added at all? Well, the reason is when the submission was made by Alex and the committee was debating it, and there were people outside the committee who were looking at it because it's a very huge submission and could have a large impact on the future of C++. People were looking at this, and Bjarne went to Alex and said, we need to add binary search to the algorithms in your proposal. And Alex said, we don't need that, it's already covered. And Bjarne said, no, we need to add binary search to the algorithms. And Alex said, well, no, we have lower bound, upper bound, equal range. We have that already, we don't need it. And Bjarne said, okay, look, here's what you're missing. He said, every software engineer in the world knows one algorithm. Some of them know a lot more, but everyone knows one algorithm. And that algorithm, of course, is binary search. So anyone looking at your library, when they look at the section of algorithms, they're looking for binary search, and they're not finding it. So they think your library, your submission must not be very good. So we need to add binary search so people know that that base is covered. And Alex said, okay, but what would it do? And Bjarne said, it doesn't matter what it does, we just need to add it. So I was in a meeting with Alex at A9, and he was talking about algorithms, and we happened to mention binary search, and Alex said, no one will ever call this because it's useless. You're going to use lower bound because it's actually more useful. And I said, well, Alex, I said, in our search engine today that Amazon uses, there's this one place where I need to know if a particular item is in the cache or not. If it's not in the cache, I'm not going to add it. And if it is in the cache, I'm not going to remove it. I just need to know, is it in the cache? And I call binary search. Now, I could have called lower bound. Why not? Why did I call binary search instead? Well, remember, I said it's a constant time operation to figure out if the value is in the range, right? Because lower bound tells you where it will be. It just doesn't tell you what it is. So all you need to do is compare the value you're looking for with the dereference iterator of where it's found. It's a constant time operation, right? What am I missing? I first have to make sure I'm not at the end of the range, right? Because it could return end, in which case I can't legally dereference it. So it's two tests, and binary search does those two tests for you. So I'm not saying it's totally useful, but I certainly agree with Alex that it's not the most useful algorithm. All right, so Alex says we don't do work and we don't do work and throw it away. And this actually impacts the library in a lot of subtle ways. I think there's things going on that people don't think about with the algorithms because of this. All right, I want to talk about, remember I mentioned that, that Alex worked for Sean at Adobe. Sean gave a talk called C++ Seasoning. And by the way, if you're not in the room right now, if you're watching the recording, if you're on YouTube, you should pause this recording right now and go listen to all of Sean's talks because they're all wonderful. And then there's a lot of them, so you'll come back in a couple of months and finish watching the rest of this talk. But in C++ Seasonings, which is a particularly good one, you could start there, Alex pointed out something about his own code. He says, I don't use raw loops. What does it mean? He's not using loops. Well, how can we do any serious work without using loops? So we process data, that's what we do, and we process data using loops. But what he's saying is that if you look at his code, you won't see any loops because what happens is we have code and then we call an algorithm. Everywhere where we're doing something that's processing a loop, the loop is embedded in the algorithm. So when he gets to a point where he's going to write a loop, he says, what is this algorithm? And it turns out, and you listen to the video, you'll see, it's surprisingly difficult when you're about to write a loop to recognize, oh, really, this is this algorithm. But what if the loop you're about to write really isn't an algorithm? And the library certainly, there's hundreds of thousands of more algorithms that are out there. The library certainly doesn't have all the algorithms. But that's good news. Why? Because you get to create a new algorithm. You get to decide what it's called. You get to rigorously define what it does. You get to write tests for it, all outside of your application. But then, when you use it in the application, you add your algorithm to your personal library of algorithms or the project or the company, or if it's really good, you put it in Boost or the standard committee. but you have added to the library of the world, right? And it's documented, it's explained, it's tested, and it's implemented really, really cleanly. That's what I would advocate. That's the discipline I use. And it's not easy. It's a discipline, but the quality of your code is much greater, and I think that's what we're trying to get to. So I'm just going to briefly talk about the structure of the STL. It has 4 components, 4 main components. There's lots of little things. Algorithms, as we mentioned, they tend to be loops. They tend to be loops that are encapsulated. And this is what, from Alex's point of view, this is the point of this library. Remember, when I first started using the STL, my thinking was, oh, it's a bunch of containers. It turns out, from Alex's point of view, no, the containers are just an implementation detail, right? Why do we have containers at all? Because algorithms have to process data. Data has to live somewhere. Data lives in containers. But we don't want the algorithms to be coupled with the containers. And so what we have is a bridge between the algorithm and the container. And that's called the iterator. And the iterator has the generic interface. It has the interface of a pointer. You want to get some information, you just dereference it. You want to go to the next one, you increment it. If it's random access, you can do pointer math on it, right? So we have a very generic interface for the iterator, but on the other hand, at the other end, the iterator may know important details about the container so that it can efficiently traverse the container, right? So the real star is the algorithm. Algorithms need data. Data needs to be put in containers, and then we use the iterator to talk to it. And then the 4th component are the callables, and they simply allow us to make code more generic. So think about find. What does find do? Find is searching for something that is a particular value. But that's a very specific case. It's a common case, but the real generic find is find if, right? Now we could have said, well, if you're looking for a value between 2 values, you could say find if between, pass in some values. Or if you were looking for something greater than a minimum, you could say find if greater or something like that. But notice we don't need all these. What we do is we just say find if, and we pass in a predicate which evaluates whatever it is that we're looking for to see if it meets our criterion, right? So using these callables is what makes things generic. And the other important thing to understand is that the STL is held together by these conventions. So conventions is container represents a sequence of value. Now you might imagine a container that was row and column. In order to get an item out of the container, you got to give it a row and a column. Well, that doesn't work. That's not our convention. So you'd have to wrap that in something that's either column-oriented or row. You'd have to make that decision. But just saying a container can be traversed from begin to end works great for most containers and is adaptable for containers it doesn't work great for. The containers also provide iterators, and we use the words begin and end and the nested type of iterator. These are all just conventions, right? But it's what makes, if we follow these conventions, it's what makes code, which is not coupled, but still interoperable. Algorithms use these iterators to define the sequence on which they work on, and these sequences are specified with half-open ranges. These are just conventions. You could imagine the STL being written with a different set of conventions, but the importance is not the particulars of the convention, but that we have established a way that all these components can work together. And if you are using the STL, my contention is you're extending the STL. You may not very often write containers, but you could write your own container. You can write your own algorithms. I suspect you'll do that a lot. You could even write your own iterator. Well, wait a minute, don't we have iterators with containers? Why would you write iterators? Well, it turns out writing your own custom iterator is sometimes very valuable. So for example, you might have, let's say, a filter iterator. What that means is I want to pass through a range, but I only want to look at the items that meet some criterion. So we make a filter iterator, which is what? It's an adapter. So it has a couple of components. One is the container iterator that it wraps. It's an iterator that actually knows how to go through a container, and a predicate to say whether or not something meets the criterion. So with our iterator, when you say plus plus, what does it do? Well, it does a plus plus on the embedded container iterator, and then it passes the data into the predicate to see if it returns true. If it does, we're done. If it doesn't, we do another plus plus. Of course, we got to make sure we don't walk off the end. So, but it's, you know, some details there, but you get the idea. Writing your own iterator in that way then allows you to add to the power of the STL. And then, of course, you're going to do a lot of function objects. Most of that we do with Lambda expressions. There are no required base classes, no virtual functions to redefine. There's no particular API. It's just you follow the conventions and you're in. And the power of this is just amazing, right? I can be writing an algorithm, and Guy is working on a container, and I don't know about his container, and he doesn't know about my algorithm, but somebody else can take them both and they work together. That's the power. Yeah, exactly right. Yes. The design is that we don't have coupling or dependency. So the algorithms, they need to know what we call the category of the iterator. We need to know, is this a random access iterator, is it a bidirectional iterator? But they don't need to know the specifics of the container they're operating on. And that's very much by design. If you write a sort iterator for DEC that's separate from a sort iterator for vector, we are getting out of the ability to reuse things generically. That's the whole point. All right, so it's been 30 years since Alex made his submission. And this has made a huge impact on our industry. I think that it's an amazing achievement. It certainly affects the way I write my code, and I think it affects the way most C++ programmers write their code. But I think there's some lessons learned. I'm gonna point out some opportunities for improvement that we probably aren't going to be able to do, because once something's in the standard, we don't change it. And I don't want you to think I'm being critical of Alex. Again, he's my idol. Most of the things I'm going to show you are things that Alex himself has pointed out after using the STL, saying, maybe we should have done better. So the first one is, this is just kind of the list of the ones we're going to go over. I got like 5 things I've called out. The first one is the name vector. What's wrong with vector as a name? What is that? Well, it's not really a vector. Guy said it's not really a vector, but I don't think from Alex's point of view that's the real issue. The real issue that there is something that's a vector. What's a vector? Right? It's a mathematical data type with direction and magnitude. And that should be called vector, but we can't call that vector because we have this data structure called vector. And Alex, being a mathematician, is somewhat offended by this. It turns out, though, Alex said, well, I didn't really name it. It turns out this was state of the art for allocated arrays. This is what people called it. And why? Well, if you think about it, remember, vector is kind of like a point with a magnitude going off this way. An allocated array, basically, we start with a point and grow it at one end. Right, so that's the idea. That's why I got that name. Kevin Carpenter was just telling me that he was doing some research on some stuff and found a submission that predates Alex's submission to the standards committee proposing a storage class called vector. So this was the name at the time. So Alex has pointed out it wasn't a great name, but he didn't have a name, a better name. I actually think AA would be a great name. It's an allocated array. Now it sounds like, well, that's pretty short, but I think vector is so important, it's going to be used a lot. And I think having a short name for something used that lot makes it a lot. But we're not going to change it. I'm not even recommending that you do a using in your, I'm not saying that. That's just something that is a lesson learned. Maybe we do think a lot about naming because it's very important. Command versus attribute. So you're all using the STL, you're all comfortable with this. If I ask you, is clear a command or an attribute? Is empty a command or an attribute? You'd know. But for someone who's first using the STL, that can be confusing, right? Which of those is a command and which is an attribute? So I think, Alex, if it was a predicate, he should have made it clear this is a predicate. Right? And again, we're used to it now. We don't think about it. But again, it's kind of we could have done a little bit better. And in your libraries, I hope you do a little better. It turns out that with the progress of time, C++ has given us a couple of tools that we can use. So we can put no discard in front of, which one would we put it in front of? Empty, right? Because if you've written code and you're calling empty and you're not doing anything with the result, you're probably expecting something to happen that's not going to happen, right? And in C++20, we can actually add a literal saying, empty is not a command, it's an attribute. Okay? All right, sort order. What is the default sort order for the STL? Less than, which is well, it's an ascending sort, results in an ascending sort. So I asked Alex about this. Why did he pick this? And Alex said, well, you want to have a default, makes things easier for when it's right. And you're obviously going to have either an ascending sort or a descending sort. And if you happen to be sorting strings, you're going to want them alphabetical. Now, I was thinking in terms of, if you were doing numbers, you probably want the big number first. If I'm looking at sales, I want to know what product sells the most. If I'm looking at population, I want to know what city's the biggest, right? But granted, if you're doing text, you probably do. So I think this is probably the right thing to decide. Anyway, there are two situations in the library where we don't follow this pattern. One is partition. So we talked about what partition is. Partition reorders things so that items where the predicate returns true comes before items where the predicate returns false. And generally speaking, we're positive people. We want the trues first. But Alex is pointing out, and this again is something Alex discovered as he was working on some sorting routines that used partition internally, that it kind of would be more consistent with an ascending sort to put the falses before the trues. Okay? Another thing that he was working on when working on sorting was max. So there's a couple of algorithms, min and max, and unlike almost all the other algorithms, they don't deal with a whole lot of data. They just work with 2 items. Pass in 2 items, and it returns the iterator to the one that is either the least for min or the most for max. That's all great. What if they're equal? Well, the standard says if they're equal, we return the iterator to the first one. I mean, you should be consistent. We should document it and say, well, we wouldn't want it to arbitrarily pick one. And if you are writing something sorting and you want to see if these items are in sorted order and you call min, then it's going to tell you if the first one is min, then that means they're in sorted order. That's true even if they're equal. But what if you call max? Well, if you call max and then you want to see that the second one is the one that's returned. But notice if they're equal, you're going to do a swap that's unnecessary. Because if the second one is returned and it says, oh, this is the greater one, then the first one's returned, then you think you need to swap because that the max is first, so you need to put them in the ascending order. But in fact, they're equal, so you shouldn't have to swap. And so Alex was just saying, yeah.
It's actually even worse, right? It also breaks stability.
It's not just doing extra work, it also breaks stability. Because if you have equal elements and not equivalent elements, they're not necessarily equal.
Right.
And then stability matters.
So not only are we doing work, we're also doing a side effect that we don't want to have, right? So that's why Alex is saying, and again, I'm not suggesting the committee change this. That would be disastrous because I'm certain there are people relying on the documented behavior. But in retrospect, being consistent is an opportunity that was missed here. So I also want to talk now about unordered containers. Oops. I wanted to ask, how are unordered containers implemented? What's the implementation of this thing? It's a hash table. It's a hash table. Now, the question is, does the standard say it has to be a hash table? In general, the standard avoids telling us how something's implemented. Gives us the behavior only. But for unordered, one of the parameters for the template is the hash function. So it kind of has to be, a hash table. So why is it not just called, why didn't we call it hash set and hash map? Why do we call it unordered set and unordered map? All right, don't spoil it. Okay, you have to set your mind back to the 1990s. The Standards Committee was very, very concerned about drug use in American youth. And so they were... No, it's not quite that bad. Alex's submission originally did have hash set and hash multiset, hash map and hash multi-map. But the problem was this. Again, taking our mind back to what the committee was faced with at the time. They were trying to ship a standard and they got hit with the huge, huge submission. And so they were trying to go through things. And when they got to the red-black trees, just regular set and map, right? Those are tree-based, very simple. If you have a comparator, then that's all you have to worry about. Very straightforward, get logarithmic performance. Hash tables are much more complicated. Why? Well, you have to figure out what's your bucket strategy. You have to figure out what's your hash function. You have to figure out, well, do we iterate over buckets? Do we care about that? There's all sorts of interesting things that you could put into the API. And so the committee, when there's all sorts of interesting things to put in an API, started arguing about things. And that drug on. And so someone came up with the compromise. They said, look, this is dragging on. We're trying to ship. How about if in the first release of the standard, we just include the tree-based things, just set and map, and we wait till the next release of the standard, which will probably be 3-4 years later, and we will then do the hash tables. Of course, nobody knew at the time it was going to be 13 years before those would come out. But they did release them in the TR1 update. But the point is, everybody knew. Nobody disagreed. Nobody was saying, who needs hash tables, right? What they were saying instead is, we can delay standardizing them because we can think about it. Let's just get this standard out. We'll come back and revisit this. But notice, who's on the Standards Committee? Well, among the people on the Standards Committee are implementers, which we love. Compiler implementers, library implementers, they give valuable feedback to the Standards Committee. They keep the committee honest. But also, the implementers of the standard library understood that hash map and hash set were coming. They saw them in the library proposal from Alex. They knew, nobody was disagreeing that they were useful. The only disagreement, was a little bit of API stuff. And so what did they do? They wanted to serve their customers, so they all created hash set, hash map, right? That was good. I think that was great. Love it. All of them, except my other idol, Howard Hinnett, made a mistake. They put them in the standard namespace. Howard didn't. He worked for a company called MetroWorks, and he put them in the MetroWorks namespace. If everybody had followed that, then when the Standards Committee got around to standardizing the hash tables, they would have just been able to say, well, the one in the STD has this API. Notice the trap that they were put in, which was that when they started to standardize, they realized, well, we could use the API that Microsoft's shipping and upset everybody in the GNU world, or we could use the API that GNU's shipping and upset everybody in the Microsoft world. Or we could do what we really want, which is to write our own API and upset everybody. And so the way they worked around that is they came up with a new name, and they said, we're just not going to use the name hash. We're going to use unordered. Okay? All right. So hash tables, the reason we like them is they have such great performance, right? We mentioned trees. Trees are logarithmic performance. That's pretty good. But what are hash tables? Order, constant time, right? Maybe constant time. In best case, constant time, right? Now, why do we not always get constant time? What takes it away from constant time? What? Collisions. That's exactly right. That's exactly right. So I'm trusting that everybody here knows a hash table. I'm going to briefly go over it, right? We are trying to have a container where the idea is we can look up in the container and know exactly where to find the item we have. So we have what we call buckets, and we put items in buckets, and what you want to be able to do in constant time, figure out what buckets you're in. So what do? We do a hash. What's a hash? A hash is a function that can take any kind of input data, but it always results in an integer. So what we do is we hash the key, we get a number, we divide the number, we mod the number by the number of buckets, and that tells us what bucket we're in. And if there's nothing else in there, that when you try to do a lookup and you're saying, find this key, boom, constant time. Nice. But there's a problem, and that is if you end up with collisions, that is multiple items in the bucket, then you go from constant time to linear time as you start looking for the item. And if you have lots of collisions, your performance gets really bad. Okay? All right, so what can cause a collision? What are the possible sources of collision? Well, one possible source of collision is that you have, when you hash, you have two different keys that create two different hash values, but when modded, they end up in the same bucket. You see how that would be a collision? Right? So how would we fix this? What do we do to address this problem? Yeah.
Single linked list. Two ways of fixing it. Either you do something like single linked list or double linked list, and you just keep stepping through until you find the item, and if it's not there and you're trying to insert, then you add it. The other way, which is in the recent Boost containers, is open addressing, whereby it's a massive array and you figure out the next location on. And that can get twice as much performance compared with linked lists.
So you're talking about how to deal with collisions. I'm talking about how can we avoid the collision, and the answer I was looking for, everything you said is true. The answer I was looking for is increase the number of buckets. If you increase the number of buckets, then you have fewer items per bucket, and so there's less likely to be collisions. So if that's your problem, that's how you solve it. But what if your problem is you have different keys, but they generate the same hash value? Now it doesn't matter how many buckets you have, the same hash value is always going to be in the same bucket. So what do we do then? Try to get a better hash function that has fewer of those. Okay, there's one other way, and that is you could have duplicate keys. If you have duplicate keys, they're of course going to generate the same hash value. They better, or we have a real problem. They're going to generate the same hash value, and then when we mod, it doesn't matter how many buckets we have, we're going to be in the same bucket. How do you fix this? That's right, you can't. You absolutely cannot fix this. So if I'm reviewing your code and you're using unordered multi, that's a red flag. I think Alex shouldn't have written that, shouldn't have proposed it. The standards committee should not have accepted it. And I think it's not even too late now for the standards committee to deprecate this. It's unavoidable, unacceptable performance. Now, maybe if you made the case, say, well, John, yeah, technically it'll be duplicates, but it's like only one item in 1,000. Okay, maybe, but just on a logical basis, it doesn't make sense to build a data structure where the performance depends on not having collisions and then saying, but of course we're going to have collisions every time you have duplicated data. Yeah. Oh, he's over here and then he'll come over there. So I wasn't going to tell this story. This whole talk, of course, is just a collection of stories. I was not going to tell this story because I'm the one who looks stupid in this story. But when C++ shipped, C++ 11, sorry, shipped, I wanted to, for a class, I was writing an example application, and I was going to rewrite it in modern code to show all the cool stuff. And I was going to shift from using the tree base to using the hash table so I could show how much faster it was too. And I hadn't even thought about this particular issue. So I was using a multi-map. So I had duplicates in my tree. And what I was doing, not a problem for a tree. But when I wrote the version using unordered multi-map, I literally, this is supposed to be faster now, right? It's a hash table instead of logarithmic. This is going to go really fast, blazingly fast. I literally aborted the program. I said, oh, I must have somehow introduced an infinite loop, but I couldn't figure it out. And I decided to give it more time and more time, and finally it finished. And I wish I was smart enough to figure it out, but I actually asked somebody else and they said, wait a minute, you have duplicate keys? I said, oh yeah, I got tons of duplicate keys. I said, well, you got no performance. And then I realized, oh, that's the problem. So what I did was I changed the payload from being a single item to being, I don't know if I used list, I probably used vector, but the point is the payload had multiple items in it. And suddenly it was lightning fast. So there is a way of approaching it, and using unordered multi is not that way. Now, you had a question over here.
Yeah, I mean, my question is, I think every algorithm has some pathological worst case kind of performance or behavior, right? Even if you're sorting, you can potentially get really terrible performance if you...
Well, I don't think any algorithm has pathological, but some do. Yeah. But what I'm saying is that this is inviting it. This is like saying, I'm making a whole data structure designed for you to shoot yourself in the foot. You know, I think, yeah. All right, and again, this isn't Alex. I never actually talked to Alex about this, and I probably should have, but this is my opinion. Okay, so one thing that Alex said that really shocked me, we were talking about the STL one day, and he says, well, the STL is out of date. And I was like, what? What do you mean out of date? First of all, I don't even see how it can be out of date. I don't know what that means. And the other thing is, I'm building my career about teaching people how to use the STL. And what I found out was, well, what he really meant is that the containers, the STL containers, were designed for systems in the 1990s. And he was telling me this, I guess it was 10 years ago, but it was long after the 1990s. He says, we were designing for the way computers worked then, and that's not a good fit for the way computers work now. Well, what's different? Anybody have any ideas what might be different? Computers in the 90s versus now? What? Oh, yeah, that's not the first one, but we'll get there. Anybody have any other idea? Threads, that's right. Okay, so the first one was malloc is more expensive. When I ask this in my classes, I say, why is malloc more expensive? Now, what he meant was relatively more expensive. Our computers are so fast today, malloc takes much less time today than it did in the 90s, but relatively, it's slower. Why is that? Well, my class always says, well, it's because we have so much more memory. No, malloc is designed to scale. More memory is not the issue. What's the issue? What is the issue, Guy? You have to block. In the 1990s, I mean, multi-threaded existed, people were doing that, but very few people were doing that because most people were just doing single-threaded applications. If you have a multi-threaded application, malloc is not reentrant, so the first thing you have to do is block. You have to take a lock. And even if you're not trying to reenter, just the taking and releasing of the lock is expensive. So that makes malloc relatively more expensive. The other thing was, he said all memory accesses have the same cost. That was the assumption we made in the 90s. And what did you say? Caching. Turns out we way more concerned about this now than in the 90s. There may have been some minor caching and processors then, but we're really concerned about it. So in 2014, when I started doing CPP-Con, I was thinking our program is great. C++ programmers are going to love this. But of course I was nervous. I'm sure Guy can relate. So I hung out in the hallway waiting for people to come out of sessions to see if they were smiling or they looked happy. And on the very first day, it was in the afternoon, I happened to catch somebody as they came out. He was talking to his buddy and he said, I get it already. It's all about caching. And apparently he'd been in 3 sessions where the person talked about the performance difference between a cache hit and a cache miss, right? We're so much more concerned about that now. So what does that mean? What that means is that we are very interested in code locality or in data locality because of the cost of loading something from memory. So what are the implications for containers? Particularly, how are we going to reduce calls to malloc? What are the containers with expensive calls to malloc? or a large number of calls to malloc. All the node-based containers, right? Linked lists, the tree containers, the hash containers, all of these have the wonderful advantage that once you put an item in one of those containers, it never moves. If I put an item in vector, it gets copied up and down depending on if I delete or add things. Things in deck gets moved around. But anything in a node-based container, once I put it in the container, as long as it's in the container, it will not be moved, even if I add things before it or after it or whatever else I might do. Because we've called malloc and created memory for that particular item. And if you had an item that's really, really expensive to copy, that could be an important thing. But the cost of that is we're calling malloc for every single element in the container. Right? That's the trade-off we're making with node-based containers. And we also want to keep data local. Well, again, with node-based containers, we're calling malloc. That means theoretically, I mean, possible, malloc could put two things right beside each other. I'm sure it happens all the time, but there's no guarantee of that. In fact, that's not even the design goal. Items can get malloced everywhere, right? We can have, page loads be called as we're trying to access items as we're walking through a container. So the advantage here is what? It's containers that use small number of mallocs per item and keep data local, right? So Bjarne, who published a book in the mid-90s called Design and Evolution of C++, he used the term default container. He said the vector is the default container. He said if you need other kinds of characteristics, fine, but the performance trade-offs with vector, the simplicity of it, that's what you should use. Now, Alex had kind of a different take on it. Alex said, if you can solve your problem with vector, you should use vector. If you can't, you should restate your problem so that it can be solved using vector. Now remember, this is the guy who implemented all the containers, but he felt so strongly that vector was the way to go, if at all possible. Now, that was their opinion in the mid-90s. Today, we like malloc even less, and we think more and more about data locality even more, right? So what's the implication here, right? The implication is that we should be thinking about containers. And again, when Alex says the STL is out of date, he's not talking about the conventions, the algorithms. He's talking about the set of containers, which remember, I told you, that's just an implementation detail, right? So my personal, you might consider something like B-tree. What is B-tree? Well, I won't go into it, but it's kind of like a node-based container, but instead of putting every item in its own node, it has small buffers. So the number of mallocs per item is not one-to-one. You have fewer mallocs, but you also have some really nice performance trade-offs. And I think Google has an open source B-tree. I don't know if anyone has ever proposed a B-tree to the standards committee, but this would be something that I would be interested in looking at, okay? All right, so those are kind of the lessons learned. And again, I'm not being critical of the STL. 30 years of setting a standard for how we should think about code. I think it's been very, very, very successful. So the last question I want to ask is, what is the STL? Now, this is from Scott Myers. Scott says, well, people might answer this by saying the portion of the standard C++ library concerning containers, algorithms, and related functionality. Or it's possible you'd say that plus strings. Remember, the string library was already standardized before Alex's proposal. But the string library has begin and end in it, right? Well, that's because they went back. The committee's not crazy. Let's think of the string as a container and let's make it work with the STL. They did the same thing with the streams library. It was also already standardized when Alex made his proposal, but they said, well, it only makes sense that we should think of these streams as possible input-output buffers. Right? And then, of course, and I didn't really mention a lot of this, but one of the things that happened, well, we know about the hash tables, but there were a lot of things that the committee just said, we don't have time. We're killing a lot of stuff. a lot of those things came back. Some of them came back in the TR1, which was released very shortly after the standard, well, a few years after the standard. But in subsequent years, we've had lots of things that were put back, or maybe we've had algorithms or other containers in Boost, the STL port. I mentioned STI, and of course, Dinkumware. All of these have created extensions to the STL that are compatible with the STL. Scott says any of those are possible answers. Some people refer to the entire standard C++ library as the STL. And I've encountered this a lot. Just talking to people, you can tell by the way they're out of context. When they mean the whole library, they say the STL. And Scott and I agree on that. No, that's just plain wrong. That's not right. So Scott says his definition is anything in the standard C++ library that supports iterators. And so that's what Alex originally proposed, and then all this stuff that's added later that has iterators in it, including things like regular expressions that you don't really think of as the STL, but it uses iterators. So you can use algorithms in the STL or in regular expressions. My definition is very expansive because I say if you're following conventions, you're using the STL. Even if it's code, maybe you haven't even checked it into GitHub, let alone into the standard. You've got it on your laptop computer and nobody else has ever seen it. But if you're following the conventions, I think that's part of the STL, right? So I have a very expansive view of this. But why is it that we have any question about this? Surely there's an official definition of the STL. Surely the standards committee said this is the STL. But no, that didn't come from the standards committee. This came from Alex. When Alex made his proposal to the committee, he put a name on it. He called it the Standard Template Library. Now this is pretty presumptuous because it wasn't accepted in the standard yet. And it also kind of meant that there wouldn't be other template libraries proposed. I don't know, but it was very presumptuous, but he called it the STL. And as the committee debated it and talked about it, that's how they referred to it because that was the name put on it. They didn't say, hey, have you heard about Alex's library? Or what do you think about Alex's library? What did you think about the generic programming proposal? No, they said, what are your thoughts on the STL? So the name stuck. But of course, now we have this weird thing. Well, what is the STL? Is it only Alex's original proposal? And I just told you my opinion of it is that if you are using conventions of the STL so that you can write code that is high quality, doesn't compromise on performance, isn't coupled with other code, solves the problem of code reusability, if that's what you're doing, then that's the STL. Anybody have any questions? Thank you.